Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, I will deliver my lecture on grade of metamorphism. I will cover this topic in two parts. In this lecture, I will proceed under the following heads: Introduction, Grade of Metamorphism. Hope it will be useful for you. Try to be regular in course. The rock of any metamorphic area were usually undergone polyphase deformation and polymetamorphism. To work out the metamorphic history of any steady area on the basis of the presence of the minerals, their assemblages and related fabrics in the different rock type. The appearance of index minerals like stolite, kyanite and sillimanite in the metaphilites, the presence of hornblende, anthophyllite, sphene and plagioclase in the amphibolite are utilized for interpretation. With the help of the concept of Barrovian zone, metamorphic phases and grade, the range of metamorphism in the area is established. In addition to the term metamorphic zone and metamorphic phases, the term metamorphic grade also impart formation about the temperature and pressure of metamorphic recrystallization. Metamorphic grade are distinguished based on a particular minerals or group of minerals that are observed. For example, the garnet zone is based on the occurrences of garnet and represent higher grade as compared to biotite zone. The grade of metamorphism referred to the intensity of the metamorphic events that a rock has suffered, and most commonly the term is used to imply the maximum temperature or pressure of metamorphism. As the temperature and or pressure increase on a body of rock, we say that the rock undergoes prograde metamorphism or that the grade of metamorphism increases. Metamorphic grade is a general term for describing the relative temperature and pressure condition under which metamorphic rocks form. Low grade metamorphism take place at low temperature and relatively low pressure. Low grade metamorphic rocks are characterized by an abundance of hydrous mineral. Example of hydrous minerals that occur in low grade metamorphic rocks: clay minerals, serpentine, muscovite and chlorite, etc. High grade metamorphism take place at higher temperatures greater than 400 degrees centigrade and relatively high pressure. As grade of metamorphism increases, hydrous minerals become less hydrous by losing H2O, and non-hydrous minerals become more common. Example of less hydrous minerals and non-hydrous minerals that characterize high-grade metamorphic rocks: muscovite, hydrous minerals that eventually disappear at the highest grade of metamorphism; biotite, a hydrous mineral that is stable to very high grade of metamorphism; pyroxene, a non-hydrous mineral; garnet, a non-hydrous mineral. Rocks crystallized under such condition would be referred to as low-grade rocks and high-grade rocks, respectively. Responses of rock to increasing metamorphic grade. Example: metamorphism of a cell made up of initially of clay minerals and quartz. Slate form at low metamorphic grade by the growth of the fine-grained chlorite and clay minerals. The preferred orientation of these seed silicates cause the rock to easily break along the planes parallel to the seed silicates, causing a slaty cleavage. Note that in the case shown here, the maximum stress is applied at an angle to the original bedding planes, so that the slaty cleavage has developed at an angle to the plane. Cyst. The size of the minerals grains tend to enlarge with increasing grade of metamorphism. Eventually, the rock develops a near planar foliation caused by the preferred orientation of seed silicate, mainly biotite and muscovite. Quartz and feldspar Grains, however, show no preferred orientation. The irregular planar foliation at this stage is called cystosity. Gneiss, as metamorphic grade increases, the seed silicates become unstable and dark-colored minerals like hornblende and pyroxene start to grow. These dark-colored minerals tend to become segregated in distinct bands, though the rock giving the rock a gneissic bending, because the dark-colored minerals tend to form elongated crystals rather than sheet-like crystals. They still have a preferred orientation with their long direction perpendicular to maximum differential stress. Gaulite, at the highest grade of metamorphism, the hydrous minerals and seed silicates become unstable, and thus there are few minerals present that would show a preferred orientation. The resulting rocks will have a granulitic texture that is similar to a phenolitic texture in igneous rocks. As temperature and pressure is fall due to erosion of overlying rocks or due to tectonic uplift, one might expect metamorphism to follow a reverse path and eventually return the rock to their original unmetamorphosed state. Such a process is referred to as retrograde metamorphism. If retrograde metamorphism were common, we would not commonly see metamorphic rocks at the surface of the earth. However, we does not see metamorphic rocks exposed at the earth's surface. Retrograde metamorphism does not appear to be common. The reason for this include slow chemical reaction. This could be due to temperature is decreased during prograde metamorphism. Fluids such as H2O and CO2 are driven off, and these fluids are necessary to form the hydrous minerals that are stable at the earth's surface. Chemical reaction take place more rapidly in the presence of fluids, but if the fluid driven off during the prograde metamorphism, they will not be available to speed up reaction during retrograde metamorphism. Winkler in 1979 proposed the three type of metamorphism or metamorphic grade, that is low, medium and high grade. Low grade, intermediate grade and high grade. Green schist, amphibolite, gaulite, and the rock change as slate to phyllite, schist, and then schist to gneiss and migmatite that show partial melting. As the degree of metamorphism increases, the new minerals become more stable and crystallize. The mineral present in a metamorphic rocks are thus indicator of the pressure and temperature condition at the time of the last crystallization. Metamorphic grade is a scale of metamorphic intensity which uses indicator mineral as geothermometer and geobarometer. Slate, phyllite, schist, gneiss, gaulite is a sequence of metamorphic rocks of increasing grade. The corresponding indicator minerals are chlorite, biotite and garnet. The transition from chlorite grade to biotite grade is the first appearance of biotite. The term metamorphic grade is widely used to indicate relative condition of metamorphism. Metamorphism may be defined as the mineralogical and textural changes which occur in a rock in response to changes in temperature and pressure imposed on it. In geology, this referred to the change in mineral assemblages and texture that result from subjecting a rock to condition such pressure, temperature and chemical environment different from those under which the rock originally formed. The word Metamorphism comes from the Greek word that is meta equal to change and morph equal to form. So, metamorphism means to change form. Metamorphic grade referred to degree or state of metamorphism. As the temperature and or pressure increases on a body of rock, we say the rock undergoes prograde metamorphism, or that the grade of metamorphism increases. Metamorphic grade is a general term for describing the relative pressure temperature condition under which the metamorphic rocks form. The pressure and temperature increases with increase of depth due to the thermal gradient. Telly in 1924 had identified 4 metamorphic grades such as very low grade, medium grade and high grade metamorphism. As the grade of metamorphism increases, new minerals become stable and crystallize. Mafic rocks, the diagnostically significant rock in very low grade metamorphism, lawsonite is one of the diagnostic minerals of very low grade metamorphism. It indicated by the first appearance of a non-sedimentary truly metamorphic minerals, and on the higher temperature side by a number of reactions, all of which have in common the formation of geolite. Very low grade metamorphism occur below 200 degrees centigrade. Very low grade metamorphism defined to comprise the temperature pressure field which is bounded on the low temperature side by the beginning of metamorphism. On grade of metamorphism part 2. In this lecture, I will cover changes from very low grade to high grade metamorphism. Hope it will be useful for you. Try to be regular in course. Changes from very low grade to high grade metamorphism. Disappearance of lawsonite and formation of geosite or clinogeosite. First, disappearance of pumpelite by reaction with chlorite and quartz producing clinogeosite beside actinolite. Second, at low pressure metamorphism where lawsonite cannot form and reaction. Third, crystallinity of illite equal to Klober law values. Fourth, low grade metamorphic rocks indicated by the beginning of green schist phases. Low grade metamorphic rocks are generally characterized by an abundance of hydrous mineral. With increasing grade of metamorphism, the hydrous minerals begin to react with other minerals and or break down to less hydrous minerals. Low grade metamorphism take place at temperature between about 400 to 450 degrees centigrade to 550 degrees centigrade and relatively lower pressure. Fifth, under the medium grade temperature ranges, the formation of schist, blue schist, amphibolite, green schist generally occur. The mineral paragenesis of low grade metamorphism, green schist phases which disappear at medium grade amphibolite phases. The mineralogical changes that characterize the beginning of the amphibolite phases, these changes should preferably occur within large pressure range. 6. Medium grade phases, the problem is mark the higher temperature boundary of the low grade metamorphic division against the medium grade division. Pressure variation play an important role in determining the stability of various minerals formed in this grade. These grades having the temperature range up to from 500 to 550 degrees centigrade to 700 degrees centigrade and is indicated by the index minerals like stolite and selemonite or cordierite. 7. Blue schist amphibolite. 8. Higher grade metamorphism generally occur at greater depth, their high pressure and higher temperature can act. It can also occur other than the higher depths where the high amount of temperature supplied by intruded magma. As grade of metamorphism increases, hydrous minerals become less hydrous by losing H2O, and non-hydrous minerals become more common. High-grade metamorphism take place at temperature greater than 600 degrees centigrade to 800 degrees centigrade and relatively higher pressure. 9. They depends on a pressure and a absence of very low partial pressure of H2O. This is significant in gamma-light terrain. A typical example indicative of high-grade metamorphism is provided by the breakdown of muscovite mica in the presence of quartz. The reaction is muscovite plus quartz give rise to orthoclase sillimanite plus water. 10. These minerals are stable only with the temperature pressure range. Consider characteristics of that particular grade. The formation of different set of minerals restricted to different grade. By study of these minerals, we can find out the metamorphic grade of the particular rock. These grades are indicated by the presence of a set of minerals that are called index minerals. Another term, isoreaction guard, is sometimes used when similar reaction as indicated by the mineral assemblages at different places in a metamorphosed area are clearly understood. In practice, an assemblage of index mineral rather an individual mineral is used for drawing isograde. This concept has been found very convenient in tracing the progress of metamorphism in the given region. Isoguard equal to line to indicate same grade of metamorphism. First appearance of minerals by increasing metamorphic grade. 12. High grade metamorphism generally occur at greater depth. Their high pressure and higher temperature cannot act. It can also occur other than the higher depths where the high amount of temperature applied by intruded magma. 13. As grade of metamorphism increases, hydrous minerals become less hydrous by losing H2O, and non-hydrous minerals become more common. High grade metamorphism take place at temperature greater than 600 to 800 degrees centigrade and relatively higher pressure. They depending on a pressure and B absence of a very low partial pressure of H2O. This is significant in gamma-light terrain. Another term, isoreaction grade, is sometimes used when similar reaction as indicated by mineral assemblages at different places in a metamorphosed area are clearly understood. In practice, an assemblages of index mineral rather than individual mineral is used for drawing isograde. The concept has been found very convenient in tracing the presence of metamorphism in the given region. Isograde equal to line to indicate same grade of metamorphism. 14. Reaction and appearance or disappearance of critical minerals can be used to determine pressure temperature condition. A grade of metamorphic rocks that have formed under the same set of physicochemical condition. Metamorphic grade is a scale of metamorphic intensity which uses indicator mineral as geothermometer and geobarometer. Increasing the grade of metamorphism is also accompanied by increasing the grain size of the rock. Telly has described as 4 type of grade: very low grade, medium grade and high grade. The degree of intensity of metamorphism that has affected a rock. is called grade of metamorphism, chemically active fluid. Dear student, today in this lecture we have discussed about the grade of metamorphism part 2. For further studies, please read the textbooks, references and links given in the text. Thank you very much.